Hello and welcome to this class. My name is Mobani Kirsten and I'm your chemistry teacher. The theme of our lesson today is chemical world and our topic is symbols, formulae and equations. The writing of chemical elements and compounds can sometimes prove to be quite lengthy and difficult. This is why symbols were introduced in order to shorten them and at the same time include as much information about the element, molecule, or compound. So, at the end of this class, you would be able to use symbols to represent elements. You know what valencies of elements are, and you'll be able to determine the valency of elements in compounds. You'd also know how to write formulae of elements, and you'd know how to derive the empirical and molecular formula of compounds. Now, symbols of elements. We say that symbols are used to represent elements. So, for example, instead of writing oxygen, we'll make use of a symbol to represent this oxygen, capital letter O. So, anywhere the letter O, capital letter O, is seen in the chemical world, it will always represent oxygen. Now, there are different symbols of elements are derived. Some elements are represented with their first letters. Some are represented by their first two letters. Some are represented by the first letter and another letter in the name of the element. Some others have their symbols derived from their Latin names. Now, we're going to take a quick look at each of them. We see that some elements are represented with their first letters. So this means that, for example, the element nitrogen, it will be represented by the first letter in that word, nitrogen. And the first letter is letter N. And we do not write them in small letter, we write them in capital forms. So other examples, we have oxygen, is represented by the letter O, capital letter O, carbon, sulfur, hydrogen, boron, nitrogen, and fluorine, and a whole lot of other elements. We also say that some are represented by their first two letters. So it means that the first two letters that make up the word of that element represents that element, or is used as a symbol for that element. For example, we have helium. As you can see, it is represented by the first two letters, which are H and E. Note also that the H is written in capital form and the E is written in small form. So this follows for other elements that have their symbols derived from two letters, such as calcium, lithium, beryllium, aluminium, neon, bromine. We then say that some are represented by the first letter and another letter in the name of the element. So, unlike the other one where we had the first two letters representing the element, here we have the first letter of the element and another letter in the word of that element. For example, we have chlorine is represented by the first letter C and another letter which is L. And so we have Cl. Also note here that the C is written in capital form and the L is written in small form. Other elements, we have magnesium, zinc, manganese, platinum, chromium, plutonium, and strontium. And then we now say that some other elements have their symbols derived from their Latin names. Their symbols are gotten from their Latin names, so it means that these elements have a Latin name, and from this Latin name, we can derive their symbols. For example, sodium. Sodium has the Latin name natrium, and from this Latin name, we derive the symbol Na. Others are iron, copper, gold, silver, mercury, potassium, lead, and tin. As you can see, these are their Latin names, and from these Latin names, we derive their symbols. You can also make your research to find out other elements that have different ways in which their symbols are derived. Now, valency of elements. From our previous class on particulate nature of matter, we said that atoms are made up of subparticles known as proton, neutron, and electron. We also say that the proton and neutron are found in the nucleus of the atom, and that the proton is positively charged, the neutron has no charge. Now, around this nucleus are the electrons that revolve around the atom, okay, or around the nucleus of the atom. Now, from that class also, we established that electrons are not just found anywhere. They are found in things we call shells. And the first shell, which is the shell closest to the nucleus of the atom, has the lowest energy. Okay? The shell next to it has a higher energy than this first shell. And there are also electrons found there. And an atom can go on to have as many shells as possible. Then, it's important for us to note at this point that when an atom or an element wants to go into combination or bonding with another element, it does so with electrons found in its outermost shell. The outermost shell is the last shell of the atom. Okay, so whenever it wants to go into bonding with another element, it does so with the electrons found in this outermost shell, and these electrons are known as valence electrons. So this is where valency of elements come in. So that valency of elements is the combining power of an element. For example, if the element sodium goes into chemical combination with another element, say chlorine, okay, with one electron in its valence shell, okay, it would mean that the combining power of sodium is 1, because when it wants to go into chemical combination, it does so with just one valence electron. So, by definition, we say that valency of elements is the extent to which an element is able to combine with other elements in a chemical reaction. And we also say that it indicates the combining power of an element. Metals will always have positive valency, while non-metals would have negative valencies. For example, the sodium we used here to explain valency, it will enter a chemical combination with chlorine. It will enter a chemical combination with one of its valence electron, which is its valence electron actually, with chlorine. And chlorine would accept just one electron from sodium. So it means that the valency or combining power of sodium is 1, and also that the valency or combining power of chlorine is 1. But because sodium is a metal, we say that its valency is what? Plus 1. And because chlorine is a non-metal, we say that its valency is minus 1. So we have here on this table some elements and their valencies. Aluminium here has a valency of plus 1. It means that aluminium is a metal, and that it goes into combination or it bonds with other elements with 3 of its valence electrons. Gold has plus 1, calcium 2. We can also see that some elements have more than one valency. For example, lead, you can see that it has a valency of plus 2 or 4. So this means that it can bond with other elements with just 2 electrons, or it can bond with 4 electrons. And we can go on and talk about the valency of different elements, because elements are constantly combining with others. Most of them are not even found in their pure states naturally. Okay, so they are always combining with other elements, and this is why it's important for us to treat valency of elements, because it is the combining power of elements. Now, there is a way we determine the valency of elements in compounds, and when we talk about the valency of elements in compound, 3 important elements come into play here. They are hydrogen, chlorine, and oxygen. So we are going to be defining valency based on these 3 elements, and we'll see how we can derive the valency of elements with which they are combined with. So we have hydrogen definition of valency. We say valency or combining power of an element is expressed in terms of the number of hydrogen atoms which combine with or displace one atom of the said element. This simply tells us that in a compound or a molecule in which hydrogen is present, you can determine the valency of the element which combines with hydrogen simply by knowing the number of hydrogen atoms that combines with that element. For example, find the valency of oxygen in H2O, that is water. So the first thing we do is we try to determine the number of atoms that are combining together. Okay, so we say we have 2 hydrogen atoms plus 1 oxygen atom. So to know the valency of this oxygen, we see that we have 2 atoms of hydrogen combining with with the oxygen. So the valency of oxygen is 2, according to this definition. Okay? Second one says, find the valency of nitrogen in NH3. So we do the same. We have 1 atom of nitrogen combining with 3 atoms of hydrogen. Therefore, the valency of nitrogen would be 3 because it is combining with 3 atoms of hydrogen. So this is just a simple way we can find out the valency of elements that are in combination with hydrogen. Then we have the chlorine definition of valency. It says that valency or combining power of an element is expressed in the number of chlorine atoms which combine with or displace one atom of the said element. So just as we saw in the hydrogen definition of valency, here it's also telling us that when an element combines with chlorine, we can find the valency of that element by simply knowing the number of chlorine atoms that combine with that element. So examples say here, find the valency of zinc in zinc chloride. And so we say 1 atom of zinc combined with 2 atoms of chlorine. Therefore, the valency of zinc would be 2 because it's combining with 2 atoms of chlorine. The second one says find the valency of aluminium in aluminium chloride. Here also, we say 1 atom of aluminium combines with 3 atoms of chlorine. So the valency of aluminium will be 3 because it is combining with 3 atoms of chlorine. Okay, it's that easy. It's that straightforward. Then we have the oxygen definition of valency. Here we just have just a slight difference, but it's still easy to understand. It's defined as, we say, valency or combining power of an element is double the number of oxygen atoms which combine with 1 atom of the said element. So here it means that to know the valency of an element that is in combination with oxygen, we'll know the number of oxygen atoms and we double that number to get the valency of the element it's combined with. For example, find the valency of magnesium in magnesium oxide. Here we have 1 atom of magnesium combining with 1 atom of oxygen. Okay, so the valency of magnesium would be 1 times 2, which is 2. Remember, it has to be double the number of oxygen atoms. So double of 1 is 2, right? So valency of magnesium is 2. Second one says, find the valency of aluminium in aluminium oxide. Okay. Here, this one is just a bit tricky, but it's just simple mathematics. Okay, so we'll find out, we'll say 2 atoms of aluminium, are in combination with 3 atoms of oxygen. So for us to know the valency of aluminium, we need to determine how much of this oxygen atom is in combination with just 1 atom of aluminium. So we say 1 aluminium atom, therefore, would combine with 3/2 times 1, which will give us this, and then it will go ahead to give us 1.5 or 1.5. So it means that one atom of aluminium is combining with 1.5 atoms of oxygen. And so 2 atoms of aluminium will be 1.5 times 2, which will give us 3. So the valency of aluminium in this compound is 3. So it's that easy. So that's how we can determine the valency of elements in compounds. Now, there are elements that combine with other elements to form more than one kind of compound. Okay? And there's also a way we name them. For example, we have these 2 elements. Okay? They are both iron chlorides. Okay? But one of them has a higher valency than the other. So how do we differentiate the 2 in writing? So what we do is we look at their valencies. All right, so this first one, iron chloride, has a valency of 3 because, as you can see, it's 1 atom of iron combining with 3 atoms of chlorine. So the valency of iron here is 3. While the second one, we have 1 atom of iron combining with 2 atoms of chlorine. So the valency is 2. So this one with a higher valency would name it by adding the suffix IC. While the one with the lower valency, we name it by adding the suffix OUS for the ferrous. So we see that, for example, if you're asked to write ferric chloride, you can now tell the difference. You know that you're supposed to write it this way. And if you're asked to write ferrous chloride, you know that the person is asking you to write this. So that is how we also go ahead to derive the name of other, compounds with varying valencies, such as mercurous chloride and mercuric chloride. As you can see, the valency of mercury here is 2, and the valency of mercury here is 1. Here is 2, here is 1. So this has a higher valency than this one. So it will be called mercuric chloride. So this is how we go ahead to derive or tell apart compounds composed of same elements but with difference in their valencies. So you can see we have mercurous chloride and mercuric chloride. This one, the mercury here, definitely has a higher valency. As you can see, it has a valency of 2. And the first one has a valency of 1. And so it's mercurous chloride, and the second one is mercuric chloride. Same also for stannous chloride. This has a lower valency than this. You can see the valency of tin here is 4, and the valency of tin here is 2. So this has a higher valency than this. And in writing, it will be called stannic chloride, while this one will be called stannous chloride. We'll go ahead to talk about the formula of elements. We say that formula of elements and compound is a simple way of representing molecules and compounds with symbols of component elements. When we started, we said that symbols are used to make it very easy for us to be able to write chemical elements, compounds, and molecules. Some molecules or compounds in writing can be very lengthy, and it won't be that easy for you to put them down. But with these symbols, okay, you can easily represent an element, represent its path in a chemical reaction, and as we said earlier too, it will be we can include as many information about that element or compound or molecule in that equation. So let's say we have sodium, okay, plus chlorine. They are reacting to form sodium chloride. Okay? So instead of writing this out, which is obviously lengthy, we can just represent them with symbols of the elements. Okay? So sodium, remember we said that the symbol for sodium is Na, plus chlorine, which is Cl, and this will give us what we call sodium chloride. Okay? So you see, we've been able to use symbols to represent this reaction, and this, in this format, is what we call chemical formula. So this is the chemical formula of sodium chloride. Okay? So we say that such representation is known as chemical formula. Now, there are some things for us to note, okay, when we are writing the chemical formula of elements or compounds. One, now, if an element exists as a molecule, okay, then the number representing its atomicity is written as a subscript immediately after the symbol. If an element is present as a molecule. Now, we established in our previous class that a molecule is simply two or more atoms that come together. Okay? Molecule is formed when two or more atoms are combined together. And then we are saying that if an element exists as a molecule, it means that the element is just that element that is forming the molecule. For example, if you have oxygen atom combining with another oxygen atom, they are going to give an oxygen molecule. So this is an example of where one element forms a molecule. Okay? And we are saying that the number that represents the number of atoms in that molecule is written as a subscript, this, immediately after the symbol representing it, but somewhere below, somewhere here. And so this 2 is telling us that we have 2 atoms of oxygen in this molecule. If we have this, it means we have 3 atoms of oxygen in this molecule. So we have other instances where we have nitrogen, hydrogen, chlorine, and ozone. Okay? So these are examples of elements that combine to form molecules. And you can see that the number of atoms in these elements are written as subscripts. Then another thing, if a molecule is composed of different elements, then the symbols representing all the elements are written close together. The first one is when an element is present as a molecule, meaning we have the same elements. Okay, but an instance where we have different elements, say magnesium and oxygen, okay, combining together to form a molecule, what happens? In writing them, we do not write magnesium separately and oxygen some other place. We need to put them together in writing like this. So this will better represent a molecule. But if they are written separately, it means we are just writing a magnesium atom and an oxygen atom. But when they are written in this form, it means that we are representing them as a molecule. Other examples, we have hydrogen chloride, otherwise known as hydrochloric acid, sodium chloride, magnesium oxide, lithium chloride, beryllium oxide. Then another thing to note is that if a molecule is made up of atoms of different elements, okay, the number indicating the number of atoms of each element is written as a subscript after the element. Okay, so it shows us that in writing a molecule or a compound, there are some elements in that compound that would have as many atoms as possible. So we need to show the number of atoms of each element in that compound. For example, if you have aluminum oxide, this is a molecule, and it is made up of different elements. As you can see, we have aluminum and we have oxygen. And then we say that the number indicating number of atoms or atomicity of each of these elements is written as a subscript. As you can see, we have 2 here and 3 here. This 2 means that we have 2 atoms of aluminum. And 3 here means we have 3 atoms of oxygen. They are not written like this. This would be wrong. In fact, this would just be showing us that maybe we have 23 atoms of oxygen, which is a very, very wrong representation of this compound. So we say that for each of the elements, immediately after that element, the number representing the number of atoms of that element in that compound is written after it. So these are simple rules when it comes to writing of chemical formula of elements. We have, for example, we have water here. This shows us that we have 2 atoms of hydrogen and 1 atom of oxygen. Obviously, we will not put 1 here. It just shows us that we have 1 atom of oxygen. Here we have 1 atom of carbon and 2 atoms of oxygen. We have 1 atom of nitrogen, 3 atoms of hydrogen, and so on and so forth. Now, in the writing of chemical formulas, we have what we call empirical and molecular formulas. We say that empirical formula is the simplest formula in which a compound can be represented. It shows the elements that make up a compound. It also shows the ratio in which these elements are present. I like to talk about empirical and molecular formulas together because it helps us to understand them better. Okay, so we say that empirical formula, it will tell us the elements that make up the compound, right? Then it also tells us the ratio in which they are present. Now, look at molecular formula. We say is the formula of a compound in which the subscripts give the actual number of each element in the formula. Now, the definitions may not make much sense, but let's just give a simple analogy to help us understand the difference between empirical and molecular formula. Let's say I use my family, as an example. So let's say in my family is made up of one father, one mother, and say 10 children. Okay, so if I tell you that, that's like the empirical formula of my family. 1 father, 1 mother, and 10 children. Now, if I come again and tell you that my family is made up of 1 father, 1 mother, 3 boys, and 7 girls. Now, look at both illustrations about my family. Both are correct, right? But one of them is more detailed than the other. Now, the first one just tells us that we have 10 children, but it doesn't tell us in detail if there are 5 boys and 5 girls, if they are all 10 boys or 10 girls. It doesn't say. But the second one gives us in details. It tells us that we have 3 boys and 7 girls. So this first representation is like the empirical formula of my family, okay? It's just telling us the elements, which are father, mother, and children. And it tells us the ratio in which they are present. 1:1:10, right? But this second one is like the molecular formula of my family. It tells us in exact form the number of boys and girls in my family. So we can have it written in this way: father, mother, boys 3, okay, girls 7. That's why we say that the molecular formula is the formula of a compound in which the subscripts, here we can see the subscripts, okay, they are giving us the actual number of each element in the formula. So it's giving us, these subscripts are giving us the actual number of the elements, or as in here now representing my family, it's giving us the actual number of family members I have. It's telling us that I have 1 father, 1 mother, 3 brothers, and probably we are 7 girls. All right? Now, I can have another friend with this same family makeup. But in her family, she may have 1 father, 1 mother, 5 boys, and 5 girls. Now you see that the empirical formula of our families are the same. 1:1:10. But our molecular formulas are different because, as you can see, you have 5 boys and 5 girls, while in my own family we have 3 boys and 7 girls. So this goes to tell us that empirical formula of more than one compound, okay, can have the same empirical formula, but in the writing of their molecular formula, we'll be able to see the difference in these compounds. Take, for instance, these three compounds, okay. You can see that the empirical formula of these three compounds are the same, CH2O, for the three of them. So with this empirical formula, we will not be able to tell these compounds apart. But in writing their molecular formula, we'll see that this compound is different from this, and this is also different from this. So we see that three compounds are actually sharing one empirical formula. So this is how we can tell apart empirical and molecular formulas. Now, when we want to solve problems on empirical formula, okay, there is a simple method involving these steps. I've put them down in this way so that it will be very, very easy for you when you have calculations that have to do with empirical formula. Okay, so the first thing you do is to convert percentage to mass. Most problems about empirical formula are given in percentage compositions. And so the first thing you do is to convert the percentage of the elements given to mass. Then the next thing you do is you convert the mass to mole. And how we do it is that we divide the reactive mass of the compound by the molar mass of the elements. After that, the next thing we do is that we divide by the smallest number gotten. Then after that, the first step would be you multiply until you get a whole number. But this step sometimes may not be needful, especially if the numbers already gotten in this step are already in whole numbers. So we are going to have a simple problem, and we'll see how we'll make use of this method to get empirical formula. So assuming you have a 100 gram of 73% mercury and 27% chlorine, find the empirical formula of the compound. Okay? So we take note of 73% mercury and 27% chlorine. So these elements have been given in their percentage composition. So we need to convert them first to their mass composition. So already we have 100 gram of the compound. So because most times we assume 100 gram of the compound. Okay? So if we have 100 grams of the compound, it will mean that 73% of mercury would be 73 grams of mercury. And 27% of chlorine would give us 27 grams of chlorine. So it's that easy to convert. Then we also have to take note of the number of, the moles of the given elements. 1 mole of mercury is 200.59 grams. If you use your periodic table, you see that. And 1 mole of chlorine is 35.453 grams. Okay? So the next step is to convert this mass to mole. And so we say reactive mass of the element in a compound over the molar mass of the element. This is our reactive mass, and this is the molar mass. So we say for mercury, we have 73. Okay? Divide 200.59. And that will give us 0.364 moles of mercury. For chlorine, we'll do the same. Have 27, divide 35.453. And that will give us 0.762 moles of chlorine. The next thing we do is we divide by the smallest number. Look at them, 0.364 and 0.762. Obviously, the smallest number here is 0.364. And so we divide both sides by 0.364. So 0.364 divide itself will give us 1. And 0.762 divided 0.364 would give us 2.09, which is approximately 2. And so for us to now, so that is it. So it's just for us to put it in the form of compounds. So we have mercury, right? Mercury is 1. And so most times we don't put 1. We just leave it as the elements. So we just have mercury there. And chlorine gave us 2. So it means we have 2 atoms of chlorine. This is the empirical formula of the compound that was given to us. So it's that easy. You can do more practical work on empirical formula to buttress your knowledge about it. So we said that molecular formula gives the actual number of atoms of the component elements in 1 mole of a compound. So as we saw previously, you can see that the molecular formula of these compounds are actually telling us how much of these elements are present in these compounds. So we have carbon, we have 2 of it here, and we have 4 hydrogen atoms, okay? Carbon, we have 1, 2, that's 2 carbons, 4 hydrogen atoms, okay, and 2 oxygen atoms. Here we have just 1 carbon, we have 2 hydrogen atoms and 1 oxygen atom. Here we have 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. So it's giving us the actual number of these elements in these compounds. Empirical and molecular formula, they are similar, as we can see, but the difference is in the value of n, okay? N is just a simple multiple. Now we are going to have a little exercise. We are going to have a small exercise to illustrate how we can find n and use n to determine the molecular formula of a given compound. Example, a compound contains 68.54% carbon, 8.63% hydrogen, and 22.83% oxygen. And the molecular weight of this compound is 140 grams per mole. Say, find the empirical and molecular formula. So we are going to find the empirical formula first, and then we use it to determine the molecular formula of the compound. So remember our steps for empirical formula. We go from percentage composition of these elements to their mass composition. Then we go from mass composition to moles, and then we divide by the smallest number, and there we have our empirical formula. So that is what we have here. These elements have already been converted to their grams. So we have for carbon 68.54, for hydrogen we have 8.63 grams, and for oxygen we have 22.83 grams. Next thing we convert to moles. Remember, we are going to divide the reactant mass of these elements by their molar mass. And doing this, for carbon we have 12.011 as its molar mass, and so we say 68.54 divide 12.011, and that will give us 5.71 moles. We do the same for hydrogen and for oxygen. Whatever figures we get, we are going to look at, okay, for our solution here, oxygen has the least number of moles. Okay, so we are going to divide every other one by that number. And so 5.71 will divide 1.43, and that will give us 3.99, or approximately 4. Okay? For hydrogen, we'll have 5.99, which is approximately 6. And for oxygen, definitely it's dividing itself, so it's just 1. And because these are all present in whole numbers already, we don't need the 4th step. Okay? We don't need to multiply by any whole number. So it means that we have, for carbon, we have 4 atoms of carbon. For hydrogen, we have 6 atoms. And for oxygen, we have just 1. So this is the empirical formula of this compound that was given to us in this problem. Having derived the empirical formula, we are going to find the molecular formula of the elements. So remember, we are given a molecular weight of 140 grams per mole. So for us to calculate the molecular weight, we are going to find the weight of the empirical formula first. So what does this weigh? We are going to just multiply these numbers by their molar masses. Okay? I already have the molar masses here in this chart. So we will say 4. So for us to do that, we'll just say 4 times 12.011 0.011. Okay, for hydrogen, we'll say 6 times 1.008. And for oxygen, we just have 1. So we say 1 times 16. So whatever we get at the end of this multiplication, we add them together. That is going to give us 70.092. That is the weight of our empirical, of this compound. Okay? That's the weight of this compound. Now, the next thing we are going to do is that we divide the molecular weight by the empirical weight. And the molecular weight given to us in this exercise is 140 grams. So we are going to divide it by the empirical weight. So that's like saying 140 divided by 70. And that's going to give us 2. So it means that the value of N is what? 2. Now we are to derive the molecular formula proper. So what we need to do is to multiply these two by the figures, by the numbers we have here for the empirical formula. So we will have something like this. We have C, 2 times 4, that's 8. So we have C8. 2 times 6, that is 12. So we have H12. And then 2 times 1, obviously, that is 2. So we are going to have 8 atoms of carbon, 12 atoms of hydrogen, and 2 atoms of oxygen. This represents the molecular formula of this compound. So this is a simple way we derive empirical and molecular formulas. And as I said earlier, you can keep practicing with exercises that have to do with empirical and molecular formulas so that you would get to understand this better. With this, we have come to the end of our class. We'll just take a quick recap to help us understand all we've learned today. We said that the use of symbols is a simple way of representing elements. Then we said that some elements are represented by their first letters, some are represented by their first 2 letters, some are represented by the first letter and another letter found inside the elements. And then some others are represented with symbols derived from their Latin names. And then we also said that the empirical formula is the simplest formula in which a compound can be represented. And that the molecular formula gives the actual number of atoms of the component elements in 1 mole of a compound. Now we'll just take a quick test to see how much we can remember from this class. Which of the following indicates the combining power of an element? A, mole ratio. B, valency. C, atomicity. Well, if you chose B, then your answer is correct. Valency indicates the combining power of any element. Another question, which of the following does empirical formula of compounds show? A, mole ratio. B, mass number. C, combining power. If you chose B or C, you're wrong. Our answer is A. Empirical formula of compounds. Remember, we said that it shows the ratio in which the elements are combined. With this, we have come to the end of our class. Thank you.